Hello, I'm Rolf Bergman, and it's my pleasure to walk you through this talk to the Certified Senior UVC Technician and the Certified UVC Management Professional. This chapter is on UVC measurements. It is broken into two parts. This slide is basically says that it's for, the first part is for the UVC technician, and this part concerns itself with UVC irradiance measurements. It's a prerequisite for the management professional as well, but the second part is not necessarily part of the UVC technician materials, so only the first part is for the technician. Okay, the goals for the first part is to know what the initial UVC irradiance measurements of an installed luminaire is and how to get those measurements. Understand, secondly, how irradiance is related to the UVC emitted power. This will be a kind of a more theoretical background for you to understand how radiance is related to other terms in both in lighting as well as in UVC technology. For the measurements, you're going to be using portable measuring instruments that have a detector and a separate readout unit. And so you will understand how to use these instruments and how to understand what the units displayed mean and record those. And finally, the units tend to be susceptible to stray light from the UVB or UVA. And so these have to be dealt with. And so we're going to talk about how to remove such stray light, and so you will understand the necessity of doing so. So the objective, if you're a technician responsible for verifying the performance and safety of the installed luminaire, after this training, you'll know what irradiance measurements are needed and how to obtain these measurements. The units will be recorded the measurements, will be recorded in specified units. And there may be a request for a given set of units from the design, and you can provide those units as requested. Otherwise, you can use the units of the readout device. And also, you will know how to take care of stray light, so your measurements will be accurate and only include the UVC part of the data. Okay, well, if you're going to make measurements and you have an installed luminaire, you need to make sure before you start measurements that things are correctly done. You need to ensure the luminaire, if it's on an upper room luminaire, usually installed on the wall, and the requirement is that the bottom of the luminaire be at least 7 feet above the floor, not lower than that. It can be higher, but normally it's exactly 7 feet. And make sure that it's installed correctly. There have been cases where luminaires have been installed upside down. That leads to all kinds of difficulties, in measurements included. And make sure that the bottom edge of the luminaire is parallel to the floor. There may be adjustments on the luminaire in which you can make sure that this happens. Also, most upper room luminaires have louvers to direct the light in a beam kind of pattern. If they have louvers, then the louvers sometimes can be rotated a bit. And so you want to make sure that they are installed correctly. So now, given that we have an correctly installed luminaire on a wall, we're going to go make some measurements on that. So first thing we're going to deal with is to check that the luminaire is functioning as specified. So you want to record the measured irradiance at 1 meter roughly, doesn't have to be exact, but 1 meter from the horizontal distance from the center of the luminaire output. And the detector is usually mounted on a pole that can be adjusted for its height. So you move the detector up and down to obtain the maximum value and record the maximum value at 1 meter. You also want to record the irradiance measurement on the wall opposite the center of the luminaire. So in line with the 1 meter, go to the opposite wall and record the maximum reading that you get on the center of the luminaire. It doesn't have to be the maximum, but record it at a given distance, like 2.1 meters or 7 feet or 8 feet. Mark that place with some sort of way so that when you come back for maintenance, you can go to that point and see if the irradiance is the same or nearly the same as it was when you first took the reading. That tells you that when you come back that the device is operating correctly. So mark that spot for maximum value and for future maintenance evaluations. You also want to take some measurements, maybe at 45 degrees, say 3 meters, or maybe at the wall, depending on how big the room is, so that at 1.8 meters from the floor and going from 1.8 to the ceiling. So you make measurements at the center and at 45 degrees, say at 3 meters or at the wall. If the wall is not much more than 5 meters, this works pretty well. You can have some judgment in where you make these measurements. But these are simply to record the data of the output, the variation in output vertically between the bottom of the loop, actually above 6 feet. So it's a foot below the bottom of the luminaire all the way to the ceiling. So that's the first set of measurements. Second set of measurements involves safety measurements. And to begin with, on the opposite wall, probably right below where you made the measurements of the highest irradiance, at 6 feet from the floor, you want to mark that for future maintenance measurements as well. This point needs to have a value of irradiance that is below that required for the safety measurements. We'll go over that in a bit. And then we want to create a grid of the floor as per the diagram shown here. It's about 1 meter or 2 feet. Lay out the room or around the room if it's a very large room. You see at the bottom, there's an Aeromed L21 in the diagram. And then at the grid points, roughly 1 meter, you find values written 0.05 at the bottom right corner, 0.09 at the, bottom left, top left, and so forth. So you will make measurements and record these values. Here, the units are not shown, but they are likely microwatts per centimeter squared. So once you have a grid laid out, you mark the floor probably with little pieces of tape or whatever is necessary, or some sort of ruler that you can use. And now you have, again, a pole or some sort of device that you can mount the unit. And that unit now, the detector stays now basically at 1.8 meters or 6 feet from the floor. And so these units will be done to evaluate whether any of those, all of these have to come in and be below an 8-hour TLV maximum exposure, cumulative dose, that is, not the irradiance, but the irradiance times the time has to be below a certain value. Okay, so those are now the measurements that we've talked about, how to make them and record them. Let me go back and talk about what the quantities are. And these are similar between lighting and invisible light and UV. But in photometry, we use lumens as the basic reference. Light of a lamp is measured in lumens. Well, in radiometry, the light, so to speak, or equivalent of light is the radiant power or the radiant flux, but it's measured in watts. The luminous flux is also sort of in watts, but it's multiplied by something called the eye sensitivity curve that you may be familiar with. So, and you notice that we now can take derivatives in a sense with respect to two parameters, either an area or at the top going angular, directional. But we're concerned here with going down directly from the picture at the top left. And you see that we're going to get the radiant power per unit area. If it's light, then this is called the luminance. It's the measured in lux. It's the Orfoot candles, which is the English equivalent. But the radiant power is going to be in units of watts per area. So say watts per meter squared, or watts, milliwatts per centimeter squared, microwatts per centimeter squared, depending on how the units are expressed. So for now, that's what we're concerned with. So we talked about irradiance in the last few slides. So irradiance then is the flux coming from the source in watts, but it's the watts arriving at the detector per unit area of that detector. Okay, there's an effective distance. Notice if I have a cone of light here, I have sort of a square cone of light. That's called a solid angle. And at a certain distance r, I kind of map out the area within that cone, and we call it A. And notice that as the cone goes from a point source, it grows. So if I'm twice as far away, I'll get 4 times the area. And if I go 4 times as far away, I get 16 times the area. This leads to an equation that says the irradiance is equal to the intensity divided by the distance squared. And in other words, the irradiance follows the inverse square law. It does this if the source is considered to be a point. So at the distance r, the size of the source needs to be very small so that the angular change doesn't do too much. So that's sorry about that. Next, we want to consider angle, and we have a radiating source and we have a detector. Now, the detectors, you're going to make measurements. Sort of looks like the detector box here. The blue shaded area is the diffused area of the detector, which receives light. And so we have the amount of light coming in through that area blue. In this case, you can consider it to be a circle. Could be a square, but let's say it's a circle. And when the detector is pointed directly at the radiating source, that is the part of the detector reads as perpendicular to the source. The blue area, notice, is perpendicular to the source. That's when you get the maximum signal, and that's the kind of what we want to have all the time. However, if you tip the detector, and there are times when we may want to do this intentionally, notice that the detector area now in one direction, in the direction that we are rotating, has become smaller. The blue arrow, I'm sorry, now represents the area in that direction, not the darker blue that we had in the first case. And that blue arrow it basically changes as the cosine of the angle E of the rotation of the device. So the detector area becomes the apparent area is the actual area of the detector times the cosine of the angle of rotation. So it is important to remember that how you orient your detector to the source will make a difference in the readings that you get. Okay, so we've looked at the effect of distance and the effect of angle on the measurement of irradiance. Now we want to look at the units. And we have, for example, suppose it was the units are milliwatts per square meter, written in MW over M squared with the 2 as a subscript. And or we may find that the detector or the requirement is that you record the data in microwatts per square centimeters. And the micro is represented by the Greek mu, usually, and centimeters is cm squared. Now we want to look at the relationship between these two. Notice that to go from milliwatts to microwatts, there is we start here, 1,000 milliwatts in 1 watt, or 1,000 microwatts in 1 milliwatt. So in the units we had above, and to go to microwatts, we need to multiply the answer by 1,000. But we also changed the denominator, the area size. We went from a square meter to a square centimeter. And it turns out that there are 10,000 square centimeters in a meter squared. So we need to divide by 10,000. So we multiply by 1,000 and then multiply by 1,000, divide by 10,000. So that's 0.1. So the conversion from 1 watt per meter squared to milliwatts per centimeter squared is 10 times less. Similarly, if you have 1 milliwatt per meter squared and go to microwatts per centimeter squared, it's 0.1 again. And keep that handy. The conversion is a factor of 10 different, depending on which way you go. Okay, let's look at the kind of equipment you're going to use for measurements. I show a calibrated, you want to use calibrated equipment. And the sensor head here that is shown on the left, notice that there's a little inset white diffuse area in the center. That's the detector. That's the detector you want to point at the device, or make it perpendicular to the luminaire that you're measuring. I go back to the calibration. There should be a calibration certificate with the detector, so that you're sure your measurements are done. If the certificate is very old, the unit may need recalibration. which is a very expensive proposition. So one way or another, the accuracy of the device needs to be ascertained. So again, the measurement, if you had a light meter and we're looking at a source to find out how many lumens per square meter or lux or foot candles there were, you do exactly the same thing. Except now, instead of getting lux or foot candles, we're going to get milliwatts per meter squared or microwatts per centimeter squared. That depends on the readout unit. And the detector is connected by a cable, fairly long cable, about 6 feet long in the case of this detector, to a readout unit. Note that the readout of this UV meter is from Gigahertz Optic, and they have a number of them that you can buy. Notice that the readout says 0.255, and it's milliwatts per meter squared. So again, if you were to convert that to microwatts per centimeter squared, you would divide it by 10, so it'd be 0.0255. This is it also tells you how it's calibrated. This one is calibrated in this case for 222 nanometer excimer. This particular gigahertz meter, by going into the menu, you can actually change what source you're looking at: low pressure mercury or LEDs of various kinds, which are peak at a given wavelength. Gigahertz Optic is one of two. The other is International Light Technologies. These two manufacturers provide UVC meters that are adequate for both safety and efficacy measurements. Efficacy measurements can be obtained by other devices, but the safety measurements are low enough and need to be accurate at a fairly low level, so that these two meters, at least in my view, are the only ones I recommend for using them. Unfortunately, they are very expensive, on the order of $2,000 and more, but that's another matter. Okay, the gigahertz unit that I showed, the 3727 detector, has a certain spectral sensitivity, and that's shown in the graph at the right. Notice that at the bottom we have wavelength starting at 200 and going all the way up to 340. The UVC region is from 200 to 280, and notice that's kind of almost in the middle. And then from 280 to 315, we have the UVB region, and then 315 up to 400 is UVA. But note that the detector sensitivity goes from the maximum to 0 right at the edge of the UVA transition. So if you have UVA light being when you're making measurements, but it doesn't come from the source, because that's a UVC source only below 280, then that light that comes from an alternate source is problematic and needs to be removed. So we note that the sensitivity curve extends to about 320. And so this is the UVB region. But if you have sunlight coming, depending on the window, coming through the window, will have some light above 290. It turns out that window glass transmission is also cuts off at about 290. So there will be some sunlight in the UVB region, a very small amount that comes through the glass. But we're talking about very small amounts to start with, so this may be a problem. So you have to avoid windows during the day, and At least check to see if they are important. Some glass is different than others. Furthermore, if you have fluorescent lamps in the room, they have mercury lines at 303 and 313 in the UVB region, which are not completely cut off by the glass of the bulb. So even though they're fluorescent lamps and don't emit any UVC, they do emit a little bit of UVB. And that little bit, again, if it's in the line, if you're measuring under a fluorescent lamp, then that's a problem. Some cases, some covers on fluorescent lamp, which use plastic, usually take this out, so that makes it less of a problem. But whatever you do, you need to check with the source off where you're measuring to make sure that there's no reading on the detector with zero offset. If there is zero offset, then you can correct it by doing, in the case of setting offset to be the continuous wave background. It'll subtract whatever reading you have. I didn't mention that LEDs, if they're quite bright at 450, even have a tail that we can see the tail with the gigahertz meters. So even LEDs have to be carefully accounted for. So how do you get rid of it? Well, you turn off the overhead lights. The meter is self-lighted, and you also want to have the units, UVC unit on. If there are windows that are there, then try to put shades up. If you can't cover the window and work when the sunlight is not coming directly through the window, but is going the other direction. And as I mentioned, you can use the CW offset in the units to correct. However, the correction is only in one spot, and if you're doing multiple spots, you need to make sure that the correction doesn't change as you move. Okay, we've talked about upper room measurements, and so I want to conclude what we have done, reiterate it. We measured a specified output at 1 meter. Normally, there should be a specification with the luminaire of the reading at 1 meter from the manufacturer. You need to make sure that the reading you're getting is no less than 90% of that specified light output from the manufacturer. If it is, then I question the luminaire's how good it is. So that was the measurements above 2.1, above 1.8 meters. The measurements at 1.8 meter determines the safety. And here you notice that we took measurements in a grid, and we wrote down all those measurements. When you take the maximum reading in that grid, and you basically multiply it by 30,000, which is how many seconds roughly there are in a day. So so that multiplied value of the irradiance times 30,000 has to be less than 6 millijoules centimeter squared for if it's a low pressure mercury lamp, or 10 millijoules if you're concerned with the skin, but mostly it's the eye we're concerned with. So the 6 millijoules per square centimeter is kind of the limit. That's if the luminaire is a low pressure mercury, which most of the cases are. If they're LEDs, then that value probably, and if the radiant output is above 254, then the 6 millijoules likely becomes 3 millijoules. So you only have half as much for the TLV as needed. Okay, one final thing we want to talk about. Devices have come in the market the last few years that can be mounted in the ceiling for whole room installation. They have, and we talked about the sources in chapter 2, is called excimer sources, and particularly krypton chloride radiates at a peak at 222 nanometers. These units are made to mount on the ceiling, pointing the radiation down. Some of the units create kind of a beam. Others have a diffuser over them, so the beam is kind of spread over most of the room. But whatever, we'll assume that we have a source that's mounted on the ceiling and pointing down. So now the measurement procedure is different. If the ceiling is below 10 feet, then record the measured irradiance at 0.5 meter from the center and directly below the source. If it's 10 feet or higher, you can record the irradiance at 1 meter, which is the standard from the UV RP procedure, where you want to measure these. But either one, 0.5 or 1 meter distance, and record that. That's the maximum that you're going to be concerned with. So in addition, and they may be very close to that, record the measured irradiance at 1.8 meter from the floor directly below the source. That may be a little over 1 meter, it may be less than 1 meter, but it should be more than 0.5 meter. So, and that is the measurement you compare with the TLV. You also want to record the radiance at 1.3 meters from the floor directly below the source. The 1.8 is for someone standing. The eye level is about 6 feet of a tall person. 1.3 meter is for someone sitting. The reason we want to make a difference is that we don't expect a person to stand for 8 hours, but we may expect a person to sit for 8 hours directly below the source. But in any case, all you need to do is record the values, and with the director pointing up at the source. We also want to make the measurements at 1.8 meters from the floor with the detector now pointed horizontally. Now it's actually 90 degrees, so you're with respect to the source. And you also want to have a 80-degree cone, if possible, on the detector. This is important because you want to simulate what the eye sees, and the eye doesn't see 180 degrees. Remember, the eye is sunk in a socket, and the eyelid above it is particularly such that light doesn't come into the eye until you get within 40 degrees of normal to the eye. So that's why the 80-degree cone. So you want to record the irradiance and in many directions and from many spots, sort of like similar to the grid, but not necessarily in a grid, to make sure that the light bouncing off the walls or coming at a steep angle from the sources themselves are not above the maximum. So the conclusion then is that we have we measured the irradiance in a room, and if we measured it multiple places, we can kind of get an average irradiance. There's other ways to get the average irradiance that are better, but that average irradiance needs to be there are requirements on susceptibility of microorganisms to irradiance values, and generated by UVC luminaires in the low wavelength region, like the eximers, that will say that the luminaire is effective and it's still safe. So let me reiterate that last bit. So we want to determine that the maximum dose is below the TLV, which is put out by a group called ACGIH, American Congress of Gynecologists, and I forgot. Anyway, UV the dose at 222 nanometers, which is the eczema peak we talked about for skin, is 478, and for the eye, it's 160. So notice that they're almost exactly a factor of 3 apart. The skin can tolerate 3 times higher dose or exposure level. So an example now, we talked about the 30,000 seconds. So if I have 16 microwatts per square centimeter average values at 1.8 meter from the floor for people standing for 8 hours, then that will put me in at 480 basically. 30,000 times 16 microwatts becomes 480 millijoules. So notice that, so when you're measuring the irradiance, you want to make sure that it's below 16 at 1.8, if the assumption is that that's for people standing. It needs to be recorded in any way. The skin TLV limit is used in practice because, as we talked about, if this luminaire is ceiling mounted and the eyelid is protected from looking directly at the source, and you're not going to be looking up that much of the time. So certainly a factor of 3. The exposure to the eye is usually on the order of 10% that of the skin, but it needs to be less than 30% to apply the skin TLV. The eye TLV can be done and will be required probably by some organizations. So the summary now of all the things in part 1. We recorded the irradiance values so that we can verify that the unit is behaving as the manufacturer says it should. We've also recorded irradiance values in a grid or multiple places to make sure that the installation is safe for occupants. The safe level is different depending on which luminaire type you use. And we've talked about the portable instruments that you use for these, and they should be calibrated and set for the type of UVC lamp measured. And you need to check for stray light to make sure that it's taken into account, either subtracted or done away with. Thank you.